Yes.
Should we get started? Hello. Hey.
You can go it over. There's actually another one.
Oh, sure. Yeah. Hello, everyone. We're going to get started now. Welcome to the first meeting of the Privacy Enhancements and Assessments Proposed Research Group. I'm Shivan Sahib. My co-chair, Sarah Dickinson, unfortunately couldn't be here, but she's on Jabber and Meetecho and all those things. And Melinda very graciously offered to help us. So thank you, Melinda. So we have 4 presentations today. And we try to get a good mix of open source, academic, as well as civil society folks who work on privacy. And the idea is that by next meeting or so, we would also have work items to be looking at. This is Notewell. You've probably seen this about a dozen times by now. And the idea, you should probably take a look at it. It has patent information as well as code of conduct and a bunch of really useful links. Do we have a JavaScribe? Thank you. And Corinne offered to take notes. Thank you, Corinne. That was easy. So we had our side meeting in Montreal, where we heard a lot of opinions and thoughts on where we should be taking the research group. And this is the first meeting. And we've already had a lot of discussion on the charter, on the mailing list. We also made some modifications based on that discussion, but we wanted to keep 10 minutes at this meeting to talk about if there's any more opinions and thoughts on the charter and the research group in general. So if there's any comments, those are welcome right now. Else we can also get 10 extra minutes. Yeah, Nick Doty. Hi, Nick, you should be able to speak now. We can't hear you, Nick.
Yeah, wait. Hi, Nick. We can't hear you. It's not clear if it's something in this room or at your end. The AV guy's not here. Nick, if you relay your question to the Jabber room, we can, if you type your question into the Jabber room, we can relay it to the floor.
Yeah, the charter is approved, but just in case, we just wanted to keep some time to maybe go over the discussion or if anyone had extra thoughts on it.
Okay, so Nick's question, which he did, which was not prefaced with Mike, is just curious about the status. Is this already approved and settled? What kind of feedback are you looking for now?
Yeah. So the charter was approved, but again, we just wanted to see if there's any further opinions and thoughts or on the discussion itself as well. Hi, yes. Mike, is it on?
Thank you. Nalini Alkins. I'm confused. Are you asking for comments now, or are you going to ask for comments later? Or
so we already got comments, but if you have any comments, you can make them right now.
Okay. Yeah, are you looking for? I guess my comment is a more, I guess, a generic. Is like, how are you defining privacy? Is it just privacy of protocols or privacy in platforms, or in a more general sense, or what? I guess I'm not because there's different implications. Depends on how you define privacy, right? Yeah. So that's a question for you guys, or maybe the group.
Right. Yeah, we did go over this a little bit, but I think the idea is that protocols primarily, but also it's a research group. So we do have, we want to be able to like get different opinions on, like, as you said, application layer, all that stuff as well.
So then one thing I might suggest is Tim Cook had a wonderful speech that he gave at the EU discussing some of the implications of privacy, in particular, the amount and quantity and quality of data that's collected by some of the large platforms and is monetized. So I don't know if that has any place in this charter or not.
Thanks. If there's no further comments, we can move on to the first presentation. Is it?
Yeah, there's a comment from Nick. I thought it was notable that privacy beyond just confidentiality was highlighted, but no particular research items or topics seem to be suggested.
Right. I mean, the first meeting we tried to get, we tried to do some outreach for like groups that we thought were doing interesting research on privacy and work around privacy. But I mean, like you said, that's definitely like in scope, and we would be interested in looking at that. Okay, so we can move on to the first presentation by Bennett.
Hello. Hi, everyone. My name is Bennett Ciphers, and I'm a new staff technologist at the Electronic Frontier Foundation. So I'll start off with quick, if you've never heard of EFF, we are a member-funded nonprofit. We fight for privacy, free expression, and innovation. And we have over 40,000 dues-paying members worldwide who support us. So I'm going to start off this presentation. This is going to be a presentation about Privacy Badger, which is our browser extension privacy protection tool. And I'm going to give a little context first. So this is about how we came to build the tool that we built. And it's also a story about protocols and how sometimes they're not enough. So some of you may have been involved with this fight, and please feel free to kind of interrupt with questions or anything if you want. I want to keep this relatively informal because it's going to cover a lot of ground, and I'd like to see what kind of discussions can come out of it. So anyway, back in 2008 and 2009, some people came up with the idea. This is the corporate surveillance on the internet was kind of coming more into the popular consciousness, and people were getting upset about it for the first time. Well, larger group of people was getting upset about it for the first time. And so this idea that maybe there could be a way for consumers to actually opt out of tracking. The internet didn't have to work that way. Not everyone had to be tracked all the time. And some ad companies actually thought this might be a good idea too at the very beginning, because they thought they might be able to head off some of the consumer backlash against them by agreeing to not track a small group of people who would opt into this do not track idea. So in 2009, a group of researchers proposed the first version of the DNT signal. This is a header that gets sent with every request for a resource over HTTP, and it was implemented as a Firefox extension, and it gained momentum really quickly. In 2010, the FTC made a call for a universal DNT system that tech companies and browsers could adopt, and it got adopted very quickly. A working group was chartered at the W3C. By the end of 2011, pretty much every major browser had support for this opt-in DNT signal. You could go into the settings, say, I want to send DNT with every request that I send. And in 2012, the Digital Advertising Alliance, which is this giant industry group that represents many of the biggest digital advertisers, said, we are going to respect the DNT signal because this is a way that we can avoid further regulation. And everything looked great around this time, around the beginning of 2012. And then some things changed. Some people got a little zealous. Internet Explorer 10 and Windows 8 decided to launch, IE10 launched with DNT turned on by default. That was the express settings. And IE back in 2012 was still, I don't know if they were still the biggest browser, but they were still massive. Chrome hadn't come to dominate the entire market yet. And so this was huge. All of a sudden, the number of people who had opted into DNT went from like single digits to low double digits percentage to like a very significant chunk of the web. Many people who never would have thought about tracking at all otherwise. And the Digital Advertising Alliance immediately backed out. Google, Yahoo, a bunch of other companies started putting in their policies. We don't know how to honor DNT. We don't know what it means. We're not going to respect it at all. And that's when we at the EFF, who, well, not me, other people at the EFF who had been working on this were like, things are breaking down. This is not going anywhere. We need another way to try and allow people to opt out of tracking. And that's when we started developing Privacy Badger. And then just as sort of an epilogue, about a month ago, the final charter for the W3C DNT working group expired and there was absolutely nothing to show for it. So, Privacy Badger, what the idea of it was, it was born out of this wish for users who didn't want to be tracked to have some sort of way to opt out of tracking. And so it's a non-consensual tracker blocker. We wanted to obviously provide users with a technical means of blocking trackers. We also wanted to spread awareness about tracking and DNT at the time. We were hoping we could still sort of salvage that as a viable means of opting out. We wanted to promote our idea of DNT compliance and what it should mean for a company to respect DNT. And we wanted to also just kind of have a stick to go along with the DNT carrot to punish companies who didn't respect the DNT signal coming from users' browsers. But we were a nonprofit organization at the time. We had very few coders on staff, and we didn't want to become a software company in order to make this happen. So it had to be built by a very small group of people. It also had to be easy to use and cross-platform. We really wanted this to be a high-impact tool. And the final constraint was we didn't want to use a block list. We didn't want to do the same thing that every other tracker blocker out there does, which is just have a curated list of these are all the things that we know do tracking, and we're going to stop them. And that's for a couple of reasons. Mainly, we didn't want to have that sort of editorial responsibility, but also we were thinking like, in the wrong hands, a block list is a censorship tool. If anyone were to ever compromise our motivations or surreptitiously force us to do something, that could effectively be used to block off big parts of the internet for all of the people who trusted us and used Privacy Badger. So, what did Privacy Badger become and what is it now? Basic mechanics, Privacy Badger it's a non-consensual tracker blocker. So the first thing it does, it turns on DNT in your browser. It sends a DNT signal to every site and every resource that you request. And it looks for a DNT policy posted at /well-known/dntpolicy.txt on every domain that your browser visits. And so anytime you fetch a resource, it'll first check to see whether the domain that hosts that resource has a DNT policy posted. And if it does, and if it's one of the policies that we acknowledge as being a respectful policy, we will allow resources from that domain to do whatever they want. So they can perform actions that might otherwise look like they're tracking actions because we trust that this legally binding policy, that they will follow this legally binding policy and not use the data that they collect to track you. If there is not a DNT policy and if it looks like a domain is taking a tracking action, we will learn to block that domain. And so Privacy Badger uses heuristics to identify trackers. So at the very beginning, when you have a fresh instance of Privacy Badger, it doesn't block anything. All all it has is a set of actions that identifies as tracking actions. And as you browse around the web, it will try and learn which domains take these tracking actions and then block them in a third-party context from there on out. And the basic mechanic is 3 strikes and you're out. So if you are browsing around and you see, if Privacy Badger sees the same resources from the same third-party domain on taking tracking actions on 3 separate first-party domains, it will mark that domain as a tracker and block it from there on out in any third-party context. So what is a heuristic? We kind of went for the low-hanging fruit. Luckily, there are a lot of very low-hanging fruit in the tracking world. The first one is just third-party cookies. Third-party cookies are still used everywhere, even though there are a lot of tools to block them, and they're relatively easy to opt out of. So we consider any third-party cookie with sufficient entropy to be a tracking cookie. We also look for local storage reads and writes with sufficient entropy. Those are basically the same as cookies. And canvas fingerprinting. We have a couple different heuristics to identify more common types of canvas fingerprinting, and we detect and block that as well. So we had to make some compromises to keep the scope relatively contained. The first one is we assume that each domain, each top-level domain +1, so that's like google.com and not like mail.google.com, or it's like anything underneath google.com, is either a tracker or not. So once you identify like subdomain.tld as tracking, it also identifies everything under the TLD +1 as tracking as well, unless the company has posted a do not track policy on some subdomain in particular. And we're also assuming that outright blocking resources from domains that perform tracking usually won't break first-party sites, and that's just a usability thing. We have to go on this assumption, otherwise the tool is kind of inviable and dead on arrival. And so for when these assumptions break down, we have a few different workarounds. The first one is cookie block domains. That's sort of a middling in between outright blocking resources and outright allowing resources. The second is we have a feature called widget replacement, which I'll talk about later. And finally, we just have user control. So every action that Privacy Badger learns to take against every domain can be configured and changed by the user if they want. And so that gives them the power to debug issues on sites and to block trackers that Privacy Badger might not otherwise catch. First, I'll talk about cookie block domains. These are domains that Privacy Badger has decided are trackers, but we have also determined are unfortunately essential for the operation of a significant number of sites on the web. So these sites are not allowed to perform local storage reads or writes. They're not allowed to set or get cookies. We strip the referrer header from all requests to these domains. And the way these domains are propagated is we just have what's called a yellow list, which is every domain that we have manually identified as being something that's essential to the function of big parts of the web goes on this yellow list. And this is a curated list, and it's all goes to our GitHub. And this is the main vector that we have to resolve broken site issues. So someone says, oh, everyone who's using Privacy Badger is breaking my site. And so then we'll allow them to make their case to get on the yellow list. And this rests on the assumption that blocking access to these functions almost never breaks a site. Like if you have something that relies on google.com, if you block these certain functions for scripts that come from google.com, most of those sites should still work. And that turns out to be pretty reliable in practice. Next, widget replacement. This is a really cool feature. And it comes from some research that happened at the University of Washington back in 2011, 2012. So this is just, we identify certain widgets and like add-ins from third parties that are common across the web that also happen to perform tracking. So like the Facebook like button is the most common one. Every time you see a Facebook like button, that has sent Facebook your login cookies. They know that you visited that site. But it also is a useful feature for a lot of media sites. And so we have this we have this feature where we identify that a Facebook like button is going to be loaded, and we instead insert our own resource that looks like the Facebook like button, but we don't allow the Facebook like button to actually load. So no request goes out. Our resource is there. But then the user can click on our resource and opt in to being tracked by the Facebook like button, but also opt to access the functionality that goes along with that tracking. So we have that for SoundCloud as well. Yeah, certain sites need cookies, like so putting them on the yellow list isn't enough to get them to work. Other sites need refers, that kind of thing. This is a bit labor intensive. We have to do a good deal of work to build each one of these widget replacements, but it is really effective, and it's a great way to deal with things like buttons and embedded media. Finally, the ultimate fallback is user controls. So if you open up Privacy Badger in your browser, the little tooltip, you will see a list of all the third-party domains that have been loaded on the site that you're on, and the ones that Privacy Badger has identified as tracking, the actions that it's taken, whether it's being blocked outright or being cookie blocked, as well as all the domains that it doesn't think are tracking. And you can manually set what actions you want Privacy Badger to take for those domains in the future. So finally, I'm going to talk a little bit about the kinds of things that we're doing to move beyond Privacy Badger's original core mission, and the things that we're looking at down the road as where we might have to take it. The first one, and this is an ongoing effort, and it's kind of been around from the start, is limited first-party and software-specific features. So like the big one is outgoing link tracking. So if you've ever used social media, Twitter, Facebook, like on Twitter, you'll notice that every link that you tweet is wrapped in a t.co link. And so that has a dual function of shortening the URL. Twitter says it adds security features, but more importantly, it allows Twitter to see every time you leave their site, where are you going? Facebook, Google do the same thing. There's a little less transparent. We have some pretty cool blog posts about how those features work and how Privacy Badger's counter features actually work to stop them. And this is a thing that, while it's not quite third-party tracking in the original sense that Privacy Badger was designed to block, it is third-party tracking in the sense that users understand it. It's like you're taking an action to leave a site, and that site really shouldn't have anything to do with where you're going afterwards. And so users feel that this is something that Privacy Badger should block. Another one is we are trying to build heuristics to identify what we call first to third-party tracking. These are trackers like Google Analytics. So the way Google Analytics works, they don't use any third-party cookies. Every site that uses Google Analytics sets up its own first-party Google Analytics cookies, and then has JavaScript which makes requests to Google Analytics with the values for those first-party cookies in the URL parameters. So it's not quite as easy for Google to link one user who visits two different sites with Google Analytics enabled to link those two visits together, because they don't have the same like cookie ID that's persistent. But obviously there are a lot of other ways to correlate those two visits for Google. Once you've made two requests from two different sites, like if your IP doesn't change, which it usually doesn't, they can link those visits, or like they can use TLS session resumption things, or just TLS sessions in general. So we're working on features to identify and block those. And web beacon requests are another thing. This is a relatively new feature in HTML. It allows sites to set up asynchronous requests that go out when a user takes a specific action on a web page. That might be clicking on a link, or navigating away from a page, or doing something else. And they're pretty much exclusively designed to do tracking. And so we're going to start considering those requests, tracking requests as well, when they go out to third parties. We are working on features to strip URL tracking parameters like UTM and the new FBCLID. Fingerprint randomization, instead of just blocking fingerprinting scripts from loading, we might try and start randomizing fingerprints when they happen in a first-party context. And finally, detecting and blocking screen recorders. There's a whole new class of companies that do things like you can install their JavaScript on your page, and it will record every movement that your users take on that site, and then you can like replay them and stuff like that. And they're almost never disclosed on the sites that they're used. And so this is the kind of thing while it is first-party tracking, most users would like to opt out of it if they could. And so we're trying to figure out how to block that. The next kind of direction we're taking Privacy Badger is a thing we call Badger Set. And this is just a sort of observatory in which we use Privacy Badger to map out the trackers on the web. So we just have a cloud computer instance with running Selenium, like a headless browser, and we have Privacy Badger installed on it, and we browse around the web and measure all the trackers that Privacy Badger sees and identifies on its trip around the web. And we'll visit a few thousand to like 10,000 sites. And the other thing this allows us to do is ship Privacy Badger with not a curated block list, but a pre-trained list. So it's a list. It means the first time a new user installs Privacy Badger nowadays, they will block most common trackers because it's as if they've been browsing through all these common sites. And it's all heuristic based, but it does ameliorate the problem we used to have, which is people would install Privacy Badger, go to a web page and be like, oh, it's not blocking anything, like it doesn't work, and then immediately uninstall it. And it also allows us to test out new heuristics and measure their impact on the web. So this is just the result of a recent scan we did on the top 10,000 sites on the Majestic Million. And these are the most common trackers we identified. Facebook.com was by far the most common. They use third-party cookies everywhere. They have the Facebook pixel on, as you can see, around a third of the popular web. Google was the second most common. Twitter, it's all of the social media companies these days. But it's really mostly a two-horse race, sort of a three-horse race if you count Twitter. DoubleClick, of course, is also owned by Google. And this is the result of a test of our new cookie sharing pixel heuristic, which is designed to identify that first to third party tracking case and to catch specifically Google Analytics. And so as you can see, we identified 70 something instances of Google Analytics tracking on the scan. We also identified a few other companies that are using similar techniques. And finally, the last thing that we're kind of have on the horizon is Privacy Badger Mobile. And that's because the web is no longer really the primary way that most people interact with the internet. Mobile browsing and mobile apps are really starting to eclipse the sort of mind share of people's activity on the web. And it is much, much more difficult to block trackers in mobile apps. They're in these little siloed software environments where you can't really install an extension into most apps. They're protected by the operating system. And it's very difficult to detect and block trackers within these environments. The only way you can really do it is with a VPN. Using the VPN API, you can have like a VPN that just sort of grabs every request before it leaves your phone, and you can filter things there. But thanks to the rise of other great privacy features like HTTPS and in the future DNS over HTTPS and stuff like that, it's going to be really difficult to filter traffic even in a VPN environment. And so obviously we're not advocating for people to roll back the progress we've made with HTTPS, but it does present these unique challenges for like, it's great that the NSA can't surveil people, but it's going to be a lot harder to stop corporations from surveilling people in environments like this. Anyway, I think I might have used up a little too much time.
That's fine.
But if anyone has any questions.
Hi there, this is Daniel Kahn-Gilmore from the ACLU. Thanks for this work. This is awesome stuff. One of the things I wanted to mention about the Badger set is that you actually have an additional feature that you didn't mention in your list for Badger set. And that is that Privacy Badger as a learning tool modifies the user's behavior on the basis of their history. And modification of behavior on the basis of history is one of the fundamental patterns that we're used to seeing for tracking mechanisms. So this is one of the issues with HSTS, for example, is that HSTS creates a the ability to set like a meta cookie by serving someone a bunch of domains, giving some of them HSTS and some of them not, and then observing later whether they come back via HTTPS or not. So by using Badger set, what you're actually doing is you're giving people a baseline that protects them from actually having that same pattern used against them, at least with the things that you've pre-browsed. So so it's nice to know that you're giving the extra protection there. So thanks for that.
Thank you. Yeah, that's I'm not even sure we'd considered that, but that's absolutely true. Thanks.
Hey Bennett, it's Corinne from the Oxford Internet Institute. So I had a question, which I'm sure you have an answer to, but it just didn't come out of your presentation, which is, so I assume that you can read all of the data of the websites that your users visit.
Yes.
What do you do with that? Because that seems like a privacy concern.
Yeah, this is, if you read the reviews on our web extensions stores, on the Chrome extension store, there are a lot of people complaining about that. We would not like to have access to all of the data on all of the sites, but the way that permissions work, it's the same thing with HTTPS Everywhere, our other extension. HTTPS Everywhere only needs access to read and rewrite URLs, but the only way to get that permission is to get access to all data on all sites all the time. And so there's very coarse-grained permissions in the web extensions environment, so we have to request the most permissive ones. But yeah, so we instrument some of the things like local storage and some of the canvas functions in order to detect tracking mechanisms. But an important thing to note is that no data ever leaves your browser and goes to EFF or anywhere else unless you send an error report. The only time your browser makes two kinds of requests to EFF. One is once a day, it makes a GET request to get the new version of the yellow list. And the other thing is if you ever decide to send an error report, it will include like the information that you tell us in the error report, but never otherwise does any information leave your browser.
Thank you.
There's an interesting discussion there as well on extension permissions in general and what the model is, I think.
Yeah, for sure. We've, there are some open Bugzilla threads about this and the problems with that in general.
Hi, Mallory Nodal from Article 19. You may not know this because you weren't around then, but I was just wondering if there was a discussion about potentially developing Privacy Badger as part of the W3C group that was on DNT. And if you didn't, why you didn't decide to do that?
That's a good question. I don't know. I can get back to you though.
Thanks.
Hi, I'm Bill Kutscher from Huawei, Germany. So I'm using Privacy Badger. Could you say something on feature interaction between different extensions, because I'm using Privacy Badger, Ghostry, ad blockers here and there.
Sure, yeah.
And I mean, unfortunately, sometimes I have to switch off one or the other. Is that something that you also consider about?
Yeah, so there's unfortunately not a lot of ways within the Web Extensions API that we can either detect that you're using other extensions or interact with them at all. So there's a problem where sometimes, like if you're using, I personally use uBlock Origin. I think it's great alongside Privacy Badger, but sometimes especially like with surrogate scripts is another feature we have, which I didn't mention. And it will, we will try and insert a surrogate script and uBlock Origin tries to do the same thing, and there's a clash and it shows you an ugly error message. And it doesn't actually break either extension, but it's a bad user experience. There's not much we can do about that, but I can tell you that most of the time they work harmoniously. Like tracker blocker extensions that use lists like uBlock or Ghostry will block a lot of things, and then Privacy Badger will block some things that they don't know to block because Privacy Badger has learned to block new things using heuristics. And that usually doesn't cause major issues. But if you have experienced specific issues, we'd love to hear about it. Please open an issue.
Hi, Giovanni Saidiana and Till Delft. So thanks for developing this and for AFF to doing that. I think it's a great tool, and yeah, thanks for that. Just a comment here. I think it was not explicit, but I like the idea. Since you don't have any telemetry data going back from the users to you guys there, the approach that I did for running a headless browser somewhere else in the cloud and do all this analysis, all those measurements, collecting all this data is a way to also obtain information, who's tracking. So I like this model of obtaining some information in an indirect way without violating the privacy of users. So yeah, I'm good.
Absolutely, thank you.
Christian Wiedemer. I always have a question when I see this approach, is that how much of a cat and mice game is it?
Yeah, that's a good question. So fortunately and unfortunately, Privacy Badger is not that big in the scheme of things. We have a few single-digit million users, but there are much bigger ad blockers, and the tracking companies, most of them operate on scales where they really just don't care about the revenue they lose from our users. So we, on the one hand, it means that we can't apply as much economic pressure as we would like against these companies, but on the other hand, it means that it's usually too much effort for them. It's not worth it for them to go out of their way to avoid Privacy Badger. And furthermore, it's pretty easy to identify new tracking methods in the wild. Like fingerprinting is basically only used to circumvent anti-tracker. Like when people decide to block cookies, fingerprinting is kind of a backup that companies can use. But it took a long time to develop a lot of these fingerprinting scripts. And once you know what to look for, it is extremely easy to look for and block these fingerprinting scripts. So I think in the end, if there is an arms race, tracker blockers and users have the advantage.
We'll be cutting the line now after people already in the line.
Taratrakia, OTF. I was wondering, do you also provide guidance for like people want to develop websites that are privacy preserving and that respect the DNT and?
Yeah, so we have a DNT policy that we have written, our lawyers have written, that's available at our .wellknown/DNT policy. And we encourage everyone to use that and read it and use that as guidance for how to respect users' data. And then beyond that, it's just generally as a site owner, the more you can limit the access you give third parties to users on your site, the better. But no, we don't have a specific guide, I don't think. That might be useful to write up though.
Marco Davids, SIDN Labs. I love the tool, thank you. I've been using it for years, but I also have an ad blocker on the same browser, and sometimes it's a little bit unclear for me who is doing what.
Mm-hmm.
Suppose I would remove the ad blocker. Would I get ads then again, even if I use your Privacy Badger? How does that work?
Yeah, you'll get some ads. So most ads perform tracking as well. But we don't block ads. Our policy is not to block ads. But most ads use tracking. And so we end up blocking most ads just kind of coincidentally. But if you did remove your ad blocker, you would probably start to see some ads in some places. And
also some content again, because more
yeah.
often I get blocked entirely because I have that ad blocker, right?
Yeah, and some more content. So the other thing is if you open up the Privacy Badger widget at the top right of your browser, you can see all the domains that Privacy Badger has identified and decided to take action on. And so like that's a kind of an easy experiment. It's like if you want to disable your ad blocker, see the domains Privacy Badger sees, and then enable it again, the difference will be what's gotten through your ad blocker into Privacy Badger.
Great, thanks.
Thanks, Bennett. Is Sophia and Jur there on the Meet Echo?
Sophia, you need to request the mic.
Can you hear me?
Yes, we can.
Cool. Great.
Great.
Can you hear me? Can you hear me?
Yes, I can also hear you.
Okay, great.
You don't hear each other. Great.
Okay, yeah.
Okay.
So you can just let me know and I'll advance the slides.
Okay, awesome. So we will start. Okay, so hi, our name is Sofia Selli and Yuri Van Bergen, and we work in Sao Paulo, Brazil, for a center that's called Centro de Autonomia Digital. And today we're going to present you all this talk that is called No Evidence of Communication, OTIB4, which is basically a presentation to introduce you of the record messaging protocol in its version 4. So next slide.
Yes. All right. So what is OTR? OTR stands for off-the-record messaging. It's an academic paper that was first published in 2004 by Nikita Borisov, Ian Goldberg, and Eric Brewer. Version 3 provides encryption with forward secrecy of all your messages, authentication, so you can be rest assured you're talking to the right person, and most importantly, deniability. Anyone can forward messages after a conversation, but during a conversation, it's assured the messages that are seen are authenticated and unmodified. Before version 3, we had version 2, which was released in 2005, and version 3 was published in 2012. More implementations followed in different languages and has seen clients or most popular operating systems. A specification was released and has been implemented in a library called libOTR, and clients pitching OTR by the OTR team. Signal created by Moxie Monenspike and Trevor Perrin, among others, drew inspiration from the OTR protocol for their Signal protocol that's been widely used by lots of people around the world nowadays. Next slide.
Okay, so basically that was a very brief introduction to what OTR is. And the consequence question that we have of that is why we need a version 4. We already have different versions of OTR. And to answer these questions, we mainly will have to look at the main purpose of OTR. The main purpose of OTR was to give deniability. So in OTR version 4, we wanted to improve these definitions of deniability. Right now, the current academic cryptographic literature has already established good definitions and types of what deniability is. We have now online, offline participation, and message deniability. And we wanted to include all of these types of different deniabilities in OTR before. What does online and offline deniability means? Deniability can be defined in the terms of OTR, not as denying a conversation, but rather as saying that anyone could have participated into that conversation. So online basically means that during the conversation, no one can actually assure that you participated or said a specific message during the conversation. Offline deniability means that after the fact that the conversation happened, no one can actually say that you participated or said a message in a conversation. And participation and message deniability basically means that you can deny having participated in a conversation or having said a specific message in the conversation.
All right, so the current state of things, currently there's a specification that's on github.com/OTRv4/OTRv4. It lists the full specification and some of the architecture decisions that have been made along the way. We also have an implementation called libOTR-ng, which is written in the C language at this point in time. Next to a library, we have a client implementation that's underway called Pitchin-OTR-ng. We have plans to package it for Debian and Ubuntu. There's also a pre-key server implementation, so you can do asynchronous encrypted communications.
Okay, so I'm sorry, my audio stopped for some reason. So yeah, as I was talking, we have different deniability properties in OTR before, and we also have different security properties that we wanted to also to have in OTR before. These kind of different properties are first and most that we wanted to raise the security level of the overall protocol to 224 by using elliptic curve cryptography. We also wanted to include the notions of forward and forward secrecy. That means that basically if you had if an attacker can compromise one of the keys used to encrypt and decrypt a message, any past and future messages would not be able to be decrypted because you only generate a key per message, a key per encrypted and decrypted the message. And we also wanted to include the notion of post-compromise security in the way that the protocol OTIB4 now has a self-healing nature, in the sense that if an attacker compromises one of the message keys, then the protocol will heal itself, and an attacker would not be able to decrypt anything else or to know the contents of anything else besides from the message that it was able to decrypt. We also wanted to include a new network model, in the sense that OTIB3 had limitations, in the sense that it was not possible to do OTIB3 in offline messaging or in an out-of-order network. And with OTIB4, we actually have offline messages and an out-of-order network. We also wanted to improve the cryptography primitives. Why? Because right now, the current academic literature has a lot of great cryptography primitives that are not used in practice. And we wanted to use these new cryptography primitives, which are secure enough for us to be used. And yeah, so basically how OTIB4 looks in the practice, you will have always two participants, which is Alice and Bob. And each one of them will say, hey, I want to use OTIB. And if they support OTIB4, they will go ahead and install the protocol. After that, you go to a section which is
Sophia, your audio cut out.
So sorry, I also just came back. Let's talk about the double ratchet. So due to the way the online way of communication through the DAKE, it's possible we can achieve asynchronous messaging like the Signal protocol through the double ratchet. So even if the other participant is offline and you still want to send them a message, when it happens, there's pre-keys at the pre-key server, which allows the user to receive messages that he's or she is able to decrypt when you're not online. And when you come online, these pre-keys will be able to decrypt the messages. So even though, and this also cuts back to the deniability part, we have two ways of doing a verification. So one of them is through SMP, which is the Socialist Millionaire Protocol, and the other one is through fingerprint verification. So through the SMP, you can actually ask the other party a question through a shared secret you have discussed before. And you are able to actually authenticate that person in question. Or if you actually already have met, you're not going to change fingerprint anytime soon, you can actually do verification through fingerprint. Next slide, please. So I think I already spoke about the specification. There's two specifications. So the field specification and some of the code is actually up on our GitHub. We actually have an implementation called libOTR-ng, which is written in the C language. We also actually have a plugin for Pitchin called Pitchin-OTR-ng. I think some of it is actually already packaged for the Arch Linux distribution. Our plan is to also package this for Debian and Ubuntu, and hopefully we can find some people to package this for us for operating systems like Fedora and others. There's a pre-key server implementation, so you can do asynchronous encrypted communication, which is through the double ratchet protocol. And there's two more implementations on the way at the moment. One in Java called OTR4J by Danny van Heumen, and one in Golang by Ola Bini, who's also working at the Centro de Autonomia Digital. Hopefully, we will see more implementations in the future that span into the mobile ecosystem as well. The great thing, of course, is that OTR v4 is not just theory or academic literature. It's quite the opposite. It's actually an applied privacy and enhancing technology that is free and open source, which cuts to the theory and practice. Next slide, please. So these are some of our Git repositories that you can find online, which actually list so the first one that /OTRv4/OTRv4 is the field specification that can be checked out. OTRv4-prekey-server is our prekey implementation that's based off the free and open source Prosody XMPP server. The library can be found, as well as the plugin for the Pigeon IM client. And next slide, please. So here we'll see the OTR NG prekey server and the other components part of the prekey implementation, as well as the toolkits, actually. And the toolkit is interesting because it allows you to actually forge the part of the transcripts after you've actually ended the conversation. All right, next slide. That's our talk. Thanks. I hope it was actually followable, even though we had some of the technical issues. Apologies for that. I'm not sure what's going on. If there's any questions, I'm happy to answer.
Great.
All right, Stephen Farrell. So there's work in IETF called MLS. Are you familiar with that? And I'm wondering how OTR4 relates to that or is different from that.
I'm not entirely familiar with the MOS. No.
Yeah.
Hi, this is Paul Vartus. So I will actually first answer Stephen's question. So MLS is a whole messaging protocol where you have lots of entities and different parties in the system that you all have to set up and run to run this protocol. While OTR is more of a add-on. So you encode on any existing message communication you have, and then you can send those encodings on. It is really lightweight. It is between two endpoints, and so you don't have all these problems that are introduced with group chat, where you have like authentication parties and revocation of keys when people join and come. And that's MLS is a huge protocol compared to the OTR.
So,
okay, can I also try to answer
yes,
about MLS? So, okay. I didn't hear the answer of the person who was just talking, but MLS, from what I have actually been reading, does not provide deniability. And one of the main purposes of OTR is actually to provide deniability. And OTR before is actually also a big protocol because it also tries to achieve security, privacy, and encryption, end-to-end encryption of all the messages, as well as forward, backwards, post-compromise security, which was also one of the aims of MLS, but also it has deniability in all of its different types. So I will say the main difference between MLS and OTR before is that OTR before has deniability and MLS does not have.
So Stephen Farrell again. Sorry, just to clarify my question. I understand the difference between OTR and kind of group messaging, like in large groups from MLS. What I don't understand is whether, one of the efforts in MLS is to try and improve the cryptographic primitives and get them, widely kind of studied by the community, by cryptographers. So it would seem that having, given that you have a lot of the same security guarantees you're looking at, it would seem like there's some benefit in having the same kind of scrutiny applied to these things.
Yeah, I completely. Okay.
Sorry, go ahead. Keep answering.
Oh, I completely agree with you. One of the aims also with OTR before was basically that it becomes also an inspiration protocol. So one of the reasons why we have OTR is that it was an inspiration protocol to other kinds of protocols, like Signal took inspiration from it, and so other protocols. So OTR before, its aim is also to be an inspiration to other protocols. So if OTR updates the cryptographic primitives, other protocols would update as well.
Kushubuk Grover, Center for Internet and Society. Sorry, it was Sophia. Your voice was breaking off at the moment, but could you just briefly explain again the different deniability properties, and specifically what does message and participation deniability provide?
Okay, sure. Yeah, I'm sorry. I'm breaking. But yeah, okay. Some participation deniability is that no one on a conversation can actually say that you participated into that conversation. No one can actually prove that. A message deniability means that no one can prove that you said a specific message during that conversation.
Eric Pascola. I have a perhaps slightly different take on this. So I think to Paul's point, I mean, I think so, like MLS and other instant messaging systems and OTR obviously have a lot of like things in common about like doing you know, the various security properties that you were just indicating. I think that so certainly like if people from OTR wish to be involved in MLS, that would be extremely welcomed. I think I speak for everybody involved in the working group on that one. I'm a little surprised about the sort of Paul's point at heavyweight. I mean, obviously, a group messaging protocol, when it's instantiated in group messaging setting, is much more heavyweight. But the actual when you scale the parameters down to one-to-one, MLS and OTR don't actually look that dissimilar. This point of deniability is kind of interesting. As you say, there are two kinds of deniability. MLS is like that makes no attempt to have deniability for these instances of communication at all. I'm not sure actually if that's even possible in a multi-party setting. I have to think about that one. MLS is just agnostic on the question of deniability for messages. That the protocols aren't well enough fleshed out to specify whether it is or it's not going to be the case. And there certainly have been discussions about making that work. So again, you know, we'd certainly love to have your participation if you're interested in working on MLS as well.
Yeah, that is awesome. We have been looking actually at some of the specification of MLS. So yeah, it will be nice to participate. And yes, of course, group chat deniability is still an unsolvable problem. Right now, there's some cryptographers that have been actually looking into this to generate some papers around it. And this is something we expect to have on previous versions of, on consequent versions of OTR.
Ben Kaduk, responsible area director for the MLS working group. Basically just seconding what Ecker said. You know, the deniability properties of MLS are not a settled question yet, so we definitely welcome further input and involvement in the working group. And you know, hopefully we can see you all there.
Great. Thanks, Jer and Sophia.
All right, thank you.
Thanks.
Next up, we have David Oliver with Pluggable Transport.
Very good. Well, thanks for the invitation here, Siobhan. So I decided that maybe the best way is to do a summary of everything here at the start, because I'm not sure how much time we'll have to get into some of the detailed things. So tries to go from high level to a little bit lower level here. So pluggable transports are a defense against internet censorship and surveillance. A pluggable transport addresses or obfuscates either the address or the contents of network flows, the primary goal being to prevent interception by intermediaries who deploy deep packet inspection. The idea of pluggable is that it's written to a specification that's being worked out actively by a small group of people interested in this area. And we need to be pluggable because the half-life of an obfuscation technology is pretty short. And the developers of those technologies and the developers of software that use them need a way to get those technologies into the field. I want to mention here a couple things. That first of all, obfuscation requires a partnership between a client and a server, or software on the device and software in the network. Pluggable transports are currently written as VPN services or as local, that is on the device proxies, or directly into built directly into applications. And pluggable at this point means pluggable by the developer and not pluggable by the end user. Just a quick point about why should we care about surveillance. You know, over time we've started to learn that surveillance runs sort of at cross purposes to individual privacy is among the core concepts we're interested in human rights. And I just wanted to note here that Guardian Project, with whom I'm involved, work mostly in mobile and mostly on mobile networks. So although there's a wider space out there, our expertise area tends to be in mobile and the opportunities and problems of the mobile operating systems and mobile networks. At the time we started this, there was a huge disparity between the privacy technologies that were available on the desktop and in mobile devices. That's changed over time, of course. Okay, deep packet inspection, for those of you who have not heard of it, when the internet protocols were designed, they were designed to route packets around the internet, but this kind of data that's produced by routers started to get used for purposes other than routing. As the technology, the hardware technology and software technology in router boxes got more and more powerful, it became possible to look at every aspect of every packet, not just the IP routing headers. So this has been rolled out over some relatively small number of years in a relatively small number of places, but it's a growing threat because, of course, you can start looking at every contents of every packet in your network. And even though we have encryption, there are still ways that there are still recognizable patterns in the packets produced by that software that allows you to know or suspect that packets are of a certain type and then start taking action on that. So, we've heard the analogy of the postman reading your mail, and even regular citizens get worried about, wow, what happened if the post office read all of my mail? So now we're kind of in that space on the internet, and some people would like to have more privacy than that, so we are working on this area. So can you defend? Yes, through obfuscation. There are two ways basically to obfuscate. One is to, I'll look at number B here first, which is that you obfuscate the intended service address. The other is to obfuscate what's actually in the packet. So, but this idea of obfuscating, first of all, requires that it gets unobfuscated before it reaches the actual service definition. It doesn't make sense to deploy obfuscation technologies that every website or every application service has to understand. So there's a transforming state and an untransforming state. But it's also important to recognize that the kind of techniques we use tend to be unsuspicious at one point and then suspicious at another point. And so obfuscation technologies are a moving target, and application developers need a way to, as I said, get their work out in the field faster. And so in roughly 2012, this idea of pluggable transports was proposed initially by the Tor project. These technologies act at the network transport layer, so applications don't see them having their effect. Applications still just continue to write and read bytes from what they think is their communication endpoint, and the transforms happen independently of that. There are three techniques. The first here, if fronting, is to obscure the address of service, and the other, scrambling and shapeshifting, actually obfuscate the data that's in your communication. The latter two are sort of demarcated when one, scrambling, is just to change the stream of bytes somehow. There are a variety of ways that have been looked at to do this, but shapeshifting is sort of a special case of that, where you are making your byte stream look like somebody else's byte stream. And in that case, maybe music streaming is deemed to be benign in today's network landscape, and so people don't surveil music streaming, whereas they might surveil something else. So shapeshifting is a subset of scrambling, but it's for a very specific purpose. So just to be clear, we do have a two-party system here, a client or software that's built on the device, and then software that exists in the network to do the obfuscation, the transform, untransform. And that's important because the application or the pluggable transport has to know where its partner endpoints are we'll discuss this a little bit further. This idea of a bridge is common to what goes on with Tor and what goes on with VPNs. And it should be noticed that these endpoints, these service endpoints in the network, or these service intermediaries in the network, pardon me, are often the targets for sensors and surveillance engines, and therefore their addresses tend to be mercurial, is a nice way to put it. Managing the configuration of these service intermediaries, these bridges, is a big problem for VPNs, Tor, and that increases with pluggable transports, since each kind of transport has to have its special kind of bridge. So there's also work underway to look at crowdsourcing bridges, that is making the number of bridges available impossible to block, but of course that means impossible to find as well. Since we're client-side people, and specifically mobile, I can really talk mostly about this. And there are two ways to implement this technology on the device. One is as a VPN, or a virtual private network. And that means that we can use an operating system interface to intercept the traffic from every application and work our magic on it. This is a very narrowly defined interface in both iOS and Android for a very specific purpose. So, and specifically the VPN style purpose that allows companies to tunnel their private traffic through the internet. Tor, however, is accessed application by application, and there are a couple of reasons for that across the different operating systems. But you'll notice that on iOS, the feature has to be bundled into the app because of the constrained process model on iOS, whereas in Android, there is an application called Orbot that is viewed as a SOX proxy by applications. So this is just a kind of very rough diagram, very simple diagram. The black line inside the blue square there means that there's a nice standoff between an application and how it's written and how the traffic is intercepted by the transports. And you'll notice that each transport has a bridge or multiple bridges, and then the application services are essentially beyond the bridges or outside the domain of the monitoring entities. So currently we have several types of obfuscation relatively easily available. Here we have Scramble Suit and Obfuscating Proxy 4. Those are the first two, and those are scrambling traffic. Meek is a transport that hides the address to which you're going, and Format Transforming Encryption is the start of something to actually shapeshift traffic. These are a little bit farther out. We're working on the latter one here, the Snowflake, which is going to work with WebRTC. Our work in the future is going to focus on systematizing or making the technology we have fit better into the operating system so that it's available for applications in a cleaner way, as well as then hopefully promoting a more standardized ability for this software to get out into the field. We're also going to look at this bridge crowdsourcing idea, as well as improving bridge configuration. This work has kind of evolved from being a Tor-only thing, where pluggability was not part of what they were trying to do for anybody besides themselves, to something where pluggability has kind of started to happen, especially once there were providers other than Tor interested in this kind of idea. There is a 2.0 specification for this, but we have to be aware that there are some pretty heavy incompatibilities within the mobile programming models that make this entire thing a challenge. So the opportunities for standardization are to look at mechanisms for delivering new obfuscation technologies at a lower level of the stack. There's also a possibility to look at ways that you could negotiate an obfuscation technology. This is, again, trying to reduce the problem of many bridges of many types. And then the latter is simply to inform allied standards, people working in this area, about the work that we're doing. Put this slide up just to advise that it's the Internews organization out of Washington, D.C. that's been funding a lot of this work. The folks here listed here are all interactive on either promulgating or doing initial and early development work in this area. Pretty simple to go to pluggabletransports.info to get virtually everything being done currently in this community. So I think that's it.
You have time for just a couple of questions?
Hi, Stephen Farrell. So I think it sounds like a fun, interesting set of ideas. Have you thought through the kind of set of tensions between scale and kind of the half-life of mechanisms here? Because it seems you're at risk of the more successful you are, the quicker you have to turn over the mechanisms.
Yeah. I know that from sort of an organizational standpoint at Guardian Project, where we started out with, literally like 2 or 3 users using our software, we do seem to be on the cutting edge of this stuff, and we expose more problems, it seems, than we solve in some ways. Now, this is good because that allows other parties to get involved and take up the activity. But this is definitely not only pluggable transports, but several of the pieces of work we've done in the past are always exposing something. There's a risk between exposing what you're trying to hide, and all this sort of work makes it tough to do in an open source world.
Right. So I mean, I guess I'm kind of wondering that's kind of an approach where you're kind of, as you scale up, maybe it gets more challenging in terms of having to get new mechanisms quicker.
Yeah.
Maybe there's another approach, which is to try make all of the normal things look the same.
Yeah, that's an interesting. We should talk a little bit about that later.
Sorry, no more questions, please. After the ones who are already there. Sorry.
You're closing the queue at the current queue?
Right after you.
After Nalini.
Okay. Ben Kadek, 2 points. One, and I don't know how relevant this is, but there's actually an IETF working group meeting in the same session right now, the Transport Services Working Group that deals with pluggable APIs for transport. I actually have no idea how relevant it is to what you're doing because I'm not an expert at either of them.
Okay.
But I would throw
Thanks
that
for
out
telling
there.
me, though.
And it's sort of interesting with DPAC and inspection. In some sense, that's just realizing the internet security model that we've been trying to use for a long time, assuming that the network is totally untrusted. And so I think there's, to some extent, intention to do, as Stephen was proposing, of trying to make the legitimate traffic look entirely uniform. Certainly in the Quick working group, that's been coming up a lot about how can we make the bulk data transport look basically random.
Yeah. Thank you.
Kathleen Moriarty. So this sounds interesting, but have you thought of the case where this is being used and both endpoints now become compromised, right? How do you detect this? Because what you're left with is your endpoint that's been compromised to reveal data. So if you bring it back to your snail mail analogy, how do you detect anthrax? How do you detect bombs?
Yeah,
And
we can
so if
talk
you're
about
eliminating all of your, so, I get the concern of protecting data. And there's lots of ways to do that, on the wire. I just want to make sure we're also considering security concerns and not just privacy, right? So how does that fit in? How can that factor in? So I'm not trying to say don't do any of this. I'm just saying think about security too.
So I would have a long answer in one way about that, so we'd better talk about that later.
Okay.
But primarily, with the earlier versions of obfuscating proxy, for example, the net effect was, haha, we figured it out, we're blocking you anyway. So, it stops working as opposed to uncovers something. Do you see what I mean? The difference? So we're not exposing anything that wasn't previously exposed. It's just that the secret got learned and it stopped working. So
No, I'm not entirely following because I'm thinking like you're using this protocol and the server end of it has been compromised and your client gets compromised.
Can we take
as a
this?
result?
Okay.
Yeah, we can totally take it
Yeah, I
offline,
think we
but I
probably
just wanted
should.
to make the point
Okay,
of I'm not
maybe
entirely
okay.
following.
Maybe I misunderstood. Thanks.
Nalini Elkins. I just wanted to kind of wonder about another tension possibly too, is that sometimes one wishes to inspect traffic for potentially benign ends, like maybe wanting to detect child pornography, something like that. I just wonder if that's something that you guys are taking into consideration.
Yeah, I can't speak for the actual implementers of this, but yeah, as I mentioned in one of the early slides, there is a tension and a problem between benign monitoring, hardcore surveillance, actual censorship, and trying to develop a technique that is sensitive to the ones that we want to block for and ones that we don't. So that's a tough challenge. Don't quite know how to answer that question directly.
Thanks, David.
Yep.
Thanks a lot. We have the last presentation by Ines. Ines, are you online?
Yeah, can you hear me?
Yes, perfect. Awesome. Go ahead.
Do you need the video? Okay. Hello. Hello, everyone. So my name is Gunesh. I'm a postdoctoral researcher at Princeton University. So I'm going to present a paper that I didn't write, which is not something I have done before. But so this is a paper that my ex-co-authors wrote, and I have also done some previous research before. So it's a paper where Lukasz, Steven, and Arvind, and it's a paper about a certain web standard called Better Status API, and assessing the privacy of web standards and standards making process using this API as a use case. So one kind of correction. So Steven is now at Mozilla, although he wrote this paper at his Princeton University capacity, let's say. And the next slide, please. Okay, so I think we can all agree that like web features and internet standards lead to privacy concerns. Next slide. For instance, take WebVR API. It's an API that allows your headset to browse internet. So next slide, please. Okay, so this WebVR API allows you to browse the web using your VR headset, and one of the things you need to do to optimize the experience is next slide to adjust your interpopular distance. This is the distance between your eye pupils. Next. Yeah, so this API actually exposes the distance between your eyes to the websites, and I think you can see it's like a privacy issue. So W3C has some measures in place to curb this or address this potential privacy issues with the web standards. And one is a self-review questionnaire. Next slide. So this includes questions that standard editors need to address when during the standardization phase. For instance, whether this standard new API that's to be introduced involves personal identifier information or high-value data. And interestingly, one of the mitigation strategies outlined in this questionnaire is, if you look at 4.3, is drop the feature. That is the removing the feature. So next. In addition, W3C has a privacy interest group called PING, privacy interest group. which among others provide guidance and advice to the during the standards development. And next. So the let me briefly talk about the Better Status API. This is a JavaScript API standards is a recommendation by W3C, and it's just a way to expose the battery information to the website via JavaScript. So it's a very simple API. The surface is just the websites can read the charge level and whether your battery is charging or not, and time, the estimate of time to charge or discharge the battery in seconds. And next. So this API first introduced in 2011 and came a long way. And after some research and research after research, basically the API is removed, basically unshipped from browsers including Firefox and Safari. So this paper is about actually what happened during this timeline. Next. So in 2012, the recommendation added this privacy and security considerations next, which said the information exposed through this API has minimal consequences for minimal impact on privacy or fingerprinting. Next, please. In 2015, researchers, including myself and Lukasz, wrote a paper, basically published a paper showing that, well, actually, a malicious website can do a lot using this API. So one is that you can just simply use the battery level, the charge level, to distinguish, for example, similar computers behind an ad. For example, in a an enterprise setting where you have a very similar computers with very similar fingerprints, and the same API, you can distinguish them, for example, using their battery level. But more importantly, we found that actually Firefox on Linux is exposing the battery level with very high precision. It's a double floating point number, and then using that and some floating point tricks, we could detect the capacity of the battery, and we propose that this can be used as a long-term identifier. Next, and later in 2016, Steven and Arvind next, please, published a web privacy measurement, web measurement of 1 million websites, and in their measurement next, they found that actually fingerprinters using this API to collect battery charge level as part of the fingerprint. So this API was found to be used in the wild by fingerprinting scripts to collect your fingerprint. So this spec, the recommendation, the W3C recommendation, was updated to address these concerns. First, they acknowledge that there might be some privacy problems, and vendors should avoid exposing high precision values, inform the user, may ask for user permission, or even choose to obfuscate or expose fake values. Next. And late 2016, which is somehow surprising, actually Mozilla started to discuss removing this API. And next, please. So the question they asked was really, is there a real website using battery API for a legitimate purpose? And they weren't convinced that there are actually, although you can do good things, there are actually they don't see a lot of uses that the original standard that envisioned as the use cases. Next. And early 2007, actually, several vendors removed or restricted the support, citing the privacy concerns and papers and the lack of use. Next, and this paper actually ran a study of like a top 50,000 websites and found that 33 websites on like more than 800 sites use this API, better API, and the majority of the users are for tracking and fingerprinting. So what happened is, so this API came out, and then several research showed there are some privacy problems, or these problems are abused in the wild, and then some vendors basically unship the API. So what we learned from this, all this, and so this paper has some recommendations, which I'll be going through in the next 4 slides. Next, please. Next. First, the specification process should include also review the implementations. So a lot of things may go wrong during the implementation, and Lukasz, one of the authors of this paper, actually involved in the privacy review of the ambient light sensors API, and they found like similar problems with the implementations where the browsers expose very high precision readings unnecessarily. Next, and so implementation is one thing, but then another problem, another question is like how the API is used. The second recommendation is actually looking into the use in the wild, and this paper says actually, so although measurement researchers can look into that, there may not also always be enough resources or time. And suggesting, for instance, browser telemetry or measurement by vendors or NGOs can help here. And the third recommendation is spec authors should take into account different threat models. For instance, audio context API is like can be used by the browser to like synthesize audio and else. This is found to be revealing the user's operating system and the browser. And in the normal standard browser case, this is something you don't care about. This is because this is already included in the user agent header. However, like Tor browser tries to hide the operating system of the user, and this is a problem for them. So take into account different threat models. And the last recommendation I have here is improve the incentives for the academics, which I think to contribute research, which I think aligns very well with the principles of this research group. So the fourth recommendation is, yeah, so next, and next, please. So yeah, basically the paper says definitely like try to incentivize attempts, try to incentivize your researchers to look into the standards and like break into the privacy assumptions, and maybe like organize workshops or forums, inviting researchers and academics to look into that. And so these are the 4 recommendations. The paper has more other recommendations as well. So next slide, please. This is the final slide. So yeah, I thank you. So you can check the paper for the other recommendations as well. And yeah, thanks for the invitation. So happy to take questions.
You have exactly 30 seconds for any questions.
Alyssa Cooper. I'll try to get it in the last 15 seconds, I guess. Thank you for this talk. I think the recommendations about measurement are pretty interesting. I participated in this work when it was very first starting, like 8 years ago, and was a person who went there and said, do not standardize this. because of these problems. There were several of us. I know that Nick is on. Nick probably remembers this maybe a little bit better than I do. But that was like the best recommendation that we could give, because there wasn't really an obvious way to represent this information in the API without having these privacy leakage problems. And essentially, like, the drive to do all of these device APIs in the W3C was so strong that those concerns were not really listened to. And then I stopped participating in the W3C, mostly for other reasons. So anyway, I just came up here to say that, to give that little bit of history, because you know, a lot of the things that you're proposing have been part of the conversation since this API was like very first proposed, and many of the other device APIs as well. And I think we have a better understanding of a lot of the threat models now, and there's a greater appreciation for these kinds of threats than there was 8 years ago. But it's still, you know, it's a back and forth.
Mm-hmm. Thank you.
Christine Runiger, W3C Privacy Interest Group Co-Chair. Thank you very much to the Princeton team. The Ping group is very grateful for that research, which gave us the opportunity to provide the feedback to the working group. One thing to mention to everyone is the security and privacy questionnaire is currently being updated. So please, if you please see me afterwards if you'd like a pointer to where to find it in GitHub so you can provide input. We also need people like the Princeton team to get involved in the work and to do the privacy reviews. And the final thing is really great recommendations. The other feedback that we're receiving too is not only should we be thinking about getting in early with the privacy discussions in the W3C, but that perhaps we should be reaching out to the browsers as they develop their tools before they bring them to be standardized. So thanks.
Thank you.
Go ahead.
Eric Rescorla. I mean, so there seems to be sort of an implicit assumption in this work. I mean, thank you for this work. I'm familiar with it. Stephen works for my company. So perhaps probably part of why we hired him. But there seems to be an implicit assumption in this work that APIs which enable this kind of fingerprinting are bad. And that doesn't really reflect, I think, the consensus of the browser vendors who basically have given up on preventing active fingerprinting largely, and think of this as something that is important to know where the fingerprinting surfaces are, and it's important to be able to suppress them for things like Tor. But I don't think that any of the major browser vendors thinks that it is practical to prevent active fingerprinting in a commodity browser implementation that has acceptable user behaviors. So if you look at what Firefox is doing, for instance, we're much more focusing on detecting misuse by sites and punishing the sites that do that than we are on trying to remove the fingerprinting surfaces.
Yeah, I felt like I can take 10 seconds response. I definitely agree. So it's actually, if it comes across like this, I think I should apologize. So it's not really that these APIs are bad, but for instance, in this case, it was like, I think, like a really downhill battle, because the exposure of this like high precision level was totally unnecessary. Whereas in other cases, you have like a legit uses of this, say, fingerprintable surface.
Sure, and I think that perhaps the lesson I would take home, and this goes back to what Alyssa was saying earlier, is for a while there was like really a rush to put like every possible API surface that like any phone programming environment had, and put that in the web somewhere, and that was done without really good cost benefit analysis to whether these things were were useful. I mean, like you'll notice that when we decided that this was bad, we didn't like reduce, the precision to 5 levels. We just removed the API entirely. So I think that the verdict on battery status API is it's useless, and that any data leak at all was a bad idea. So I think that perhaps I guess I'd be interested in your thoughts on if any way we could have made that cost benefit analysis better earlier, and realized that like there's no point, we should have added like, not only was it like bad to have a really high precision leak, but this was just like all cost and no benefit. I don't know if you have any thoughts on how we could have made that analysis earlier, but that would have been helpful.
Thanks, Edgar. We can take this to the mailing list for the comments. Thanks to everyone. That was a final presentation, and I wanted to keep some time for discussing future work items, but I guess we can do that on the mailing list. And thanks to all the presenters, and thanks everyone for coming out.
And if you haven't signed the blue sheets, we've got them up front. Thank you.